Okay, let's unpack this. Imagine standing before this ancient fortress, right? Stones steeped in centuries of history, yet you can almost see it subtly crumbling away. It's quite evocative.
It really is.
Picture this magnificent Ottoman fort, battered by the Mediterranean sun and sea, a real symbol of power, but now it's locked in this silent battle.
A battle against time, against the elements themselves.
Exactly. So today, we're taking a deep dive. It's not just about an old building. It's really about the science, the actual science of its survival.
Right.
And for you, our listener, this is your shortcut to understanding how we literally save our past one ancient stone at a time.
And what's really captivating here, I think, is how science, cutting-edge science, can actually give a voice to these silent witnesses of history.
Yeah.
Our main source for this deep dive is excerpts from this really groundbreaking paper. It's called Multidisciplinary Characterization, Weathering Patterns, and Durability Assessment. That's a long title.
Yeah, they often are.
But it's about stone blocks for conserving the Tamentfoust fort in Algiers. And this isn't just about one fort. It really speaks to the universal challenge of heritage conservation.
That fight against environmental forces everywhere.
Exactly. Relentless forces.
So our mission today, unravel these mysteries. Why is this incredible fort deteriorating? What secrets do its stones hold? And critically, how is science giving us a roadmap for its survival? We'll get into everything from its shifting identity through history to the microscopic battles happening inside its walls.
It's fascinating stuff.
Okay, so here's where it gets really interesting. The names this place has had. It tells a story in itself.
Oh, absolutely. Names carry so much weight.
The Romans called it Razgunier. Then, during the Berber Ottoman time, it became Tamentfoust, which means hand, apparently.
Yeah, in the Tamazight language. Beautiful, isn't it? Hand.
It is. Then Capmatifu under Spanish influence, and La Perouse when the French were there. So it's not just a building, it's like a living timeline.
A physical embodiment of this rich cultural evolution. And its location is key, right there on the coast, 20 kilometers east of Algiers.
So strategically vital.
Hugely. If you connect this to the bigger picture, Tamentfoust was absolutely critical to Algiers' military defenses, especially during the Ottoman period,
Protecting trade routes, fending off incursions.
Precisely, a frontline defense. Yet, fast forward to today, and the paper describes it pretty bluntly as being in a deplorable state of conservation.
Deplorable. Wow. So why? Why is this historically important, seemingly solid structure in such bad shape?
Well, part of the problem, ironically, stems from past attempts to help it.
The law of unintended consequences strikes again.
Exactly. The paper really highlights how conservation work in the 20th century often used materials that just weren't compatible. Think Portland cement mortars.
Okay, that sounds strong, but...
But it's too rigid. These modern mortars, they trap moisture, they trap sea salts inside the old stone wall.
Oh, I see. So it can't breathe.
Pretty much. It creates immense internal pressure. It's like putting a plastic wrap on a wound. It just accelerates the decay, especially in that salty marine air.
So it wasn't just using new stuff, it was using the wrong new stuff. Stuff that clashed chemically, physically.
That's the crux of it. The paper stresses this lack of understanding about physico-chemical compatibility, how the new materials would react with the old.
A major lesson learned then. You need rigorous understanding first.
It's an essential prerequisite for effective conservation today. Absolutely.
And even though it was made a National Heritage Site back in '67, turned into a museum in '99, the threats continue.
Yeah, sadly. Nearby urban development keeps adding pressure, making this kind of scientific investigation even more urgent. It really is a race against time.
Okay, so diagnosing this, it sounds incredibly complex. What does a full medical checkup for an ancient fort actually involve? Where do you even start?
Well, it really is like a medical exam, but for stone and structure. The researchers brought in geology, material science, structural engineering, conservation science. A truly holistic approach.
Couldn't just guess.
No way. They had to understand it from every angle. So they started by carefully collecting samples. 2 distinct types of stone blocks, they called them T1 and T2,
Okay.
from the damaged terrace walls. And crucially, they made sure these were from the original construction, avoiding modern repairs.
Gotcha. Get the baseline, the original material. So what did these stone patients reveal?
Under the microscope, they found T1 was a type of sandstone, quite porous, full of red algae fossils and bioclast bits of ancient sea life.
Okay, so more porous, like a sponge almost.
Pretty much. While T2 is a micrite, a much denser, fine-grained limestone, also with fossils, but different ones, like foraminifera.
So both limestones, but fundamentally different in structure.
Exactly, and that difference is key. T1, more open, more vulnerable. T2, inherently more robust. Their formation dictated their weaknesses.
Right, so once you know the basic makeup, how do you actually see the damage at that tiny level? What tools let you see the battle scars?
Well, that's where the fancy check comes in. Techniques like X-ray diffraction, XRD, and X-ray fluorescence, XRF,
Okay.
they basically give you an ingredient list, the minerals, the elements inside the stone.
Like a chemical fingerprint.
Precisely. And then for super high-resolution images of the weathering, they used scanning electron microscopy, SEM-EDX.
Wow.
This lets you literally zoom in and see these tiny, like, honeycomb patterns where the calcite is dissolving, microscopic evidence of the fight.
Incredible detail. So you know what it's made of, but you also need to know how strong it is, how it behaves.
Exactly right. So physical and mechanical properties, they measured things like density, open porosity, which tells you how much water it can soak up.
The sponge factor again.
Yep. And crucially, its compressive strength, how much pressure it takes to start crumbling it, and also flexural strength resistance to bending. And they tested how water moves through it, capillary absorption. That's a huge indicator of vulnerability to moisture and decay.
Absolutely critical for understanding its weak points.
Essential for knowing how fragile these materials really are.
And I guess you have to do all this testing without causing more damage to this already fragile structure.
That's a huge consideration. So they use non-destructive techniques right there on the fort, like ultrasonic pulse velocity testing.
Sending sound waves through.
Yeah, to check the internal structure, the coherence, without drilling or anything. And infrared thermography, too.
What does that show you?
It maps temperature differences. Cooler spots might mean hidden moisture. Warmer spots could indicate biological growth or detachment under the surface. You see problems without touching the stone.
That's clever. So what makes this particular research stand out is the combination of methods.
I think what's truly pioneering is that it's the first really comprehensive look at Tamentfoust stone in its specific coastal setting. It integrates all these methods: destructive lab tests, non-destructive field tests, and terrestrial laser scanning, TLS, for incredibly detailed 3D models.
Ah, the 3D scanning.
Yeah, which wasn't available before for this site. This whole integrated approach, it really sets a new standard for studying similar historical buildings, especially in tricky coastal spots.
A blueprint for others, then.
Mm.
Okay, so the fort's patient history is understood, its internal makeup analyzed. Now, identify the aggressors. What's attacking these stones?
Yeah, the paper really zeroes in on two main environmental threats: salt crystallization and acid exposure.
The big ones.
Definitely. And to see how the stones react, they put samples through accelerated aging tests, basically cramming years of exposure into a short time in the lab.
Simulating the real world, but faster. And the results.
Pretty stark, actually. Let's talk salt first. We know it's bad for coastal buildings.
Right, you see those white stains everywhere.
Exactly, efflorescence. But the damage goes deeper. Imagine tiny salt crystals forming inside the stone's pores. As things heat up and cool down, wet and dry, these crystals grow and shrink. They act like microscopic wedges, constantly prying the stone apart from within.
Wow, that's insidious.
It really is. The test on that porous T1 limestone, even though it only lost a tiny bit of mass, 0.65%.
Sounds durable.
Superficially, yes, but those heating and drying cycles drastically accelerated internal damage. The internal pressure weakened its compressive strength significantly.
So it looks okay on the surface, but it's crumbling inside.
Precisely. That high porosity, over 30%, makes T1 incredibly vulnerable to this hidden attack.
A silent killer for the stone. Okay, what about the acid? Is this modern pollution hitting an ancient structure?
That's exactly it. They tested the denser T2 limestone with hydrochloric acid, and the results: a 35% drop in compressive strength.
35%, that's huge.
Massive. It went from 27.57 MPa down to 17.94. Now, it didn't lose much mass, only 1.64%, but that loss of strength, that's a huge red flag for the fort's structural integrity long term.
Yeah, absolutely. So chemically, what's actually happening? How does acid or salt weaken it so much?
Well, chemically, the hydrochloric acid reacts really vigorously with calcite. which is the main component of both stones. It basically dissolves the stone's natural glue. It produces CO2 gas, water, and calcium chloride, which is soluble and just washes away. Salt does something similar. It reacts to form other soluble compounds that leach out, leaving the stone fragile.
So it's like the skeleton of the stone is being dismantled.
That's a good way to put it. Even the tougher minerals, like quartz, can slowly alter over time into weaker clay minerals. It's a constant chemical assault.
And you could actually see this under the microscope.
Oh, yeah. Some images after the tests showed etched surfaces, way more porosity, fragmented grains, basically creating little cavities and pores that physically weaken the whole structure.
Makes it brittle, less able to handle the wind and rain.
Exactly. Less able to withstand that relentless assault.
So moving from the lab back to the fort itself, they use that high-tech scanning, the TLS and infrared thermography, creating a digital twin almost.
Sort of, yeah. A detailed digital record and a thermal map.
How did that help pinpoint the problems on the actual building?
Well, the TLS 3D scan acted like a structural X-ray. It revealed what they call pathological features, all the cracks, the places where mortar was detaching.
The fort's diseases.
Exactly. Especially bad at corners and cornices, those high-stress areas. And the infrared showed temperature variations.
Right, the cooler spots meaning moisture.
Yep, hidden moisture, and warmer zones could indicate things like algae growth, creating little air pockets, trapping heat. These tools find the hidden problems, the stuff you can't see just by looking. It gives you a real diagnosis.
So where was the patient most critical? Which parts were suffering most?
There's a clear battleground area, the south facade.
Okay, why there?
It's built mostly with that really porous, soft T1 limestone we talked about, and it faces the sea, faces the port, so it gets hammered constantly.
Sun, rain, wind.
The whole lot. Relentless solar radiation, driving rain, abrasive winds carrying salt. And the mapping let them classify the damage types, almost like a medical dictionary for the stone.
What were the main ailments in this dictionary?
Well, you had the efflorescence, those white salt deposits, disintegration, where the stone just crumbles into grains, lots of biological growth, mosses, lichens.
Taking hold in the cracks.
Exactly. Microcracks from temperature changes, roots pushing in, erosion, smoothing surfaces, creating cavities, staining from pollution. But maybe the most severe was alveolization.
Alveolization sounds nasty.
It is. It covers about 20% of that south facade. It's basically severe cavity formation, like honeycombing, mostly caused by that salt crystallization and chemical dissolution of the calcite.
So it all circles back, doesn't it? The location, the type of stone.
Absolutely. The marine environment feeding it salt, the sun driving those wet-dry cycles, intensifying everything. It's just a relentless combination, a perfect storm of decay.
Okay, so we have the diagnosis, we understand the causes. What does this all mean for actually saving Tamentfoust? It seems like survival hinges on understanding this complex interplay, right?
It does. The stone's makeup, its porosity, and that harsh coastal environment. But the good news is the science also points toward solutions.
Okay, what are the recommendations?
Well, for that really porous T1 limestone, they suggest protective coatings and consolidants, things like silane-based treatments or maybe nano-lime.
To reduce water getting in.
Exactly. Reduce water ingress, make it more resistant. For blocks that are just too far gone, though, selective replacement is needed.
But with compatible stone, right? Learning from the past.
Absolutely critical. Replace with limestone that matches the properties of the more durable T2 lower porosity, higher strength, and dealing with the existing salt. Techniques like poulticing are key for drawing out that efflorescence.
Makes sense. And what about preventing future damage? Proactive steps.
Prevention is definitely better than cure here. They strongly recommend improving the drainage around the fort. Less water pooling means less infiltration, less capillary rise.
Cutting off the supply route for the salt and acid damage.
Pretty much. And also setting up a routine monitoring program using those non-destructive tools we discussed, ultrasonic testing, thermal imaging.
Regular checkups for the fort.
Yeah, to track how things are changing, catch problems early before they get critical.
And looking ahead, there's this vision for integrating even more advanced tech.
Right, this is where it gets really exciting. Imagine using machine learning, trained on all this data, to actually predict where degradation will happen next and prioritize where to focus restoration efforts.
Wow, proactive conservation.
Exactly. And they even propose creating a full digital twin of the fort, a virtual replica integrating all the data in real time.
To simulate scenarios, test strategies.
Precisely. Simulate decay, optimize conservation plans before you even touch the real stones. It's a glimpse into the future of heritage care.
And finally, making sure any new stone brought in is the right match.
Crucial. It means doing proper geological surveys to find local quarries with limestone that matches that durable T2 type, and then rigorous lab testing on those potential replacements to confirm they'll hold up in the fort's specific environment. No more guesswork. Learn from the past, test for the future.
So this deep dive into Tamentfoust Fort, it really shows us, doesn't it? Preserving heritage isn't just about admiring old buildings. It's this dynamic scientific challenge.
It really is.
It's about giving these ancient structures the kind of high-tech, informed care they need to stand for generations more, keeping their stories alive.
Indeed. And the lessons learned here, about how vulnerable certain stones are to salt, to acid, and the sheer power of this multidisciplinary approach,
Yeah.
they can be applied to countless other sites around the world. It really hammers home that understanding why decay happens is just as vital as knowing how to repair it.
So for you, our listener, maybe consider this. The next time you find yourself looking at an ancient monument, think about the hidden battles its stones might be fighting. And wonder, what untold stories of survival could modern science help us uncover there?